What do you mean compound? No, just say more.
Will there be stuff in the first midterm on the second one?
Second midterm is not before today. Today is the start of what's on second midterm. The final is cumulative. The final is everything. I want to make sure you actually learn something from everything. So don't forget. Don't just forget the first part of the semester. Hmm? Yeah. Also, if I recall correctly, the number of weeks between start of the semester and first midterm is actually bigger than second midterm is coming up sooner than you think it is. October what? October 21st. So we got, so you got 1 month. Wait, no, that's the same. That's the same. You had 1 month for the first midterm too, didn't you? Never mind. Never mind. Okay, so instead of sermoning at you, let's actually get into this. Let's do this. We're in a new module, as I said. What I want to do with this is very much cut out me talking at you. I have tried to condense the lecture portion to about 20 minutes so we can spend just as much time as possible learning by doing, which isn't to say that I won't be teaching you plenty of stuff in the exercises portion of the class. But big point is you're going to be doing a lot of physics with me very shortly. When you are doing that, please, 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 please take good notes. If I just put down everything that I will say in this lecture, this would be 500 slides, and it would be boring as heck to read. I believe in doing together and teaching by example rather than just having you read a wall of text, which means that if you're expected just to read the slides afterwards and have this make sense, you better darn well be annotating them and taking notes on them and explaining what's going on. Otherwise, this will not make sense. Yeah, so watch out. Okay, but first, I do have a few things that I will put down in words. This module is called dynamics. This is the study of forces. That is to say, it is the study of pushes and pulls. Briefly, kinematics is the science of how do we describe motion, how do things move, whereas dynamics is the science of why do things move, what makes things move, or change motion. Okay, so force is a push or a pull. Which way you are pushed or pulled matters. It's a vector. Push left, push right has a difference. If you're pushed left and pushed right, those can partially cancel. Yeah. And the harder the push, the bigger the force. Duh, right? Okay, we measure the unit of force as the newtons. Be careful. I'm also going to be writing N for a symbol referring to a certain kind of force, so normal force, a bunch. So watch out. If I write 45N, that is a measure of the strength of the force, 45 Newton. If I write N equals 45, I'm saying the variable N, normal force, is equal to 45. Be able to distinguish. This is just like, if you have 5 meters, X is 5 meters, that's different from saying M equals 3 kilograms or whatever, all right? Right? M could be used both for a unit and a name of a variable. Watch out for that. Okay, 1 Newton, don't write this down. Think about this briefly. Here's the idea of what a Newton is. If you apply a Newton to a kilo, it'll accelerate at a given rate. That's the technical definition. I don't care about you memorizing it. I want you to be able to use this, not memorize and recite, as you may have noticed. Okay, now I'm going to introduce you to the 8 big forces that we will spend 98% of our time on. I'll say a few words about each of them, more about the ones that we're going to be using more of at first. First, force is weight. Weight for what? Ha, ha, ha. Weight force. Weight, also called gravity. Here is its formula. Weight is equal to mass of an object times gravitational field of that object, m times g. Please note, weight and mass are very different quantities. Mass tells you how much of the you there is. Weight tells you how hard it's pulled
What?
gravitationally. Again, think about it.
Tucker.
Mass and weight, different quantities. Mass, how much of you there is. Weight, how hard that you is pulled by a planet or star or whatever. Okay. If I say your weight is 500 newtons, what am I talking about? The pull. I'm talking about how hard the planet is pulling you down. In deep space, do you weigh 500 newtons? No, how much do you weigh in deep space? 0. There is no gravitational force pulling on you. There is an insignificant gravitational force pulling on you between stars. Okay. Does that mean your mass is 0 in space? No, you still got inertia. Still requires a force to accelerate you. Anyway, weight is the only long-range force. Every other force we'll talk about has to have touch. That's an important point. Actually, write that down. Not just our only long-range force. Say, hint, every other force must have touch.
Okay.
So the other 7 biggies here are all touch forces. There's no contact, there's no force. Okay, friction, drag, and normal. These go together. Drag will do very little of, but it belongs sort of together with it. Friction and drag. Friction is a solid-solid interaction. Drag is a fluid-solid interaction. So drag is how you swim. Drag is, actually, I would say what opposes your swimming. I would say the pushback was the thrust. Never mind. The drag is what opposes you swimming. Why it's hard to walk through water. Drag is why you need an airplane engine, a jet turbine, or a propeller to keep you forward against the drag. As I said, drag, because Arizona is so damn conservative, and lots of people have lots of strong opinions, we're not, oh, sorry, that's a different kind of drag. Drag, the reason we don't talk about this is not gender studies raises. The reason we don't talk about this is because the equations are horrendous. You don't want to go there. Friction, we'll be doing this big time. You'll actually get 2 separate equations for friction. Friction is solid solids. Now, okay. At a certain point, I'm going to say, driving over a wet road, rubber versus wet asphalt, that doesn't contradict it. It's mostly a solid thing. Wet road is not, you're not plowing through the water. It's not inches of water. Anyway, we're doing a lot of this, but we're not doing it today, so I'm going to move on. The last thing to emphasize about friction for now is that friction is parallel to the surface. Friction is always, if I'm skimming my hands over horizontally, friction is horizontal. If I am pinning a doll to a whiteboard, the surface is pressing up and down vertically against the doll, so friction in this case is a vertical force. If I'm rubbing a balloon on my hair, horizontally, friction is the horizontal force. Drag, as I said, we're going to do very little of because the equations are god-awful. Normal force, the drag is like friction, fluid solid instead of solid solid. Normal force is intimately related to friction. Normal force is what solid solid force it directs at right angles to. Friction parallel, normal, friction parallel, normal, perpendicular. By the way, the word normal is mathlish for perpendicular.
For drag, so when we say fluid, that includes gas.
Yes. Fluid is anything that flows. Fluid is liquids and plasmas, I guess. Okay. Please note, normal does not mean every day. Normal does not mean every time. Normal just means at right angles to. Any 2 solids can exert normal forces on each other. What's the weight force formula? Mass times field. Mass times gravitation field. Good. Tension and spring go together. Buoyancy and thrust go together. Tension and spring, they're both rope forces, or string forces, or cord forces, or I guess metal coil forces. The important difference is, do you care about the degree to which something is stretchy? Technically, theoretically, if you're precise enough, every rope stretches some degree. The thing is, this cord here, the strap, I probably need a very sensitive, not a ruler, but something like a micrometer to measure the fact that this fabric is stretching, right? Whereas if I have an elastic cord, I apply the same force to it, whoa, that's a lot of stretch. So the question of, do we use a spring force or a tension force to model this is, all right, just how springy is it? And do I care about that degree of springiness? For instance, I might have a monkey dangle from one end of this, swinging back and forth. Yeah, there's a little bit of swing, there's a little bit of bounce. But who cares? The monkey is mostly just going side to side, yeah? Okay, so springing force is something that stretches and I care about the amount of stretch. Tension is I don't care about the stretch. What can exert tension forces? Strings, ropes, chains, cords, fabric lengths, metal rods, whatever. Oh, great, yeah. Buoyancy and thrust. Buoyancy, what makes a ship float? Thrust, how a propeller pushes on stuff, how a rocket engine works, how a jet engine shoves stuff behind it to push it forward. Thrust is also solid fluid. Thrust and buoyancy we're going to do relatively little of. Thrust equation is also bad. Yeah.
So as far as driving on the road, is that more heavy?
Friction. Normal is holding the car from phasing through the ground and falling to the center of the earth. The car pushing off against the ground is friction. Here's how you know it's friction. If you're on an icy, oily, slick surface, are you going anywhere? Can you gun your engine on an icy, slick road and go anywhere? It's only the existence of friction which allows us to speed up and slow down and so on. Actually, this is worth writing down, by the way. Write this down with friction. Example of friction. What makes your car do anything interesting? Speed up, slow down, turn. Right? It's a friction force that roads exert on cars. Common misconception is for people to tell me, what force acts on the car? The engine! No, the engine is part of the car. What force acts on the car? The wheels! No, the wheels are part of the car. The road that pushes on the car. Car spins the wheels. They push on the road pushes back. Anyway, we'll get to that. But I wanted to emphasize it as we went along. Emphasize it since it came along. Someone popped up and then disappeared. And tough because I can't see them anymore. Okay. So here's our dictionary of forces. Now, how do we identify which of these forces apply? It's really actually quite straightforward. Once you get the hang of it, I want you to follow these steps every time until it clicks and you really get the hang of it. Missing a force means you'll screw up the entire problem. You cannot possibly get it right. You cannot possibly get the point if you're missing a force. So, watch this carefully. Here's how to identify the forces on an object. Sketch it, and one is if there's a planet or star anywhere nearby, weight is probably important. Well, and you care about the up-down direction. If I'm talking about a car driving along a road, I might not care about the fact that it has a weight force up and down. But anyway, how do I identify the forces? If you care about the vertical direction, and I don't specifically say you're in deep space, then there's a weight. Every other force is a contact force. It requires touching. So, 2 and 3, draw a bubble around your sketch. Objects which cross the line of the bubble may exert a force. To find out what kind of force, consult your dictionary. Is it a solid-solid push force? Yeah, normal. Is it a solid-solid slide force? Friction. Is it a rope attached to something? Tension, or maybe spring. Okay? Do this every time. I will make you practice it in lecture. I want you to practice it in homework as well. Now, for the homework system, I am redoing the homework questions this year. Previously, there have been, because it is very important, there have been questions that make you draw these free body, that make you draw the force and other diagrams. There's just one thing. Computers are bad at grading if you're approximately correct. So the computers super finicky. And a lot of students get very frustrated. And as much as it really is an important skill, I also don't want to drive you batty. Just a little batty, okay? I don't want to drive you completely around the bend. So I'm taking those questions off. That means you got to promise me to actually do it yourself. Actually sketch and identify the forces carefully. You cannot possibly get problems right if you do not think clearly about what acts on it. Do this every darn time till you're good at it, till you can do it in your head. Even then, keep doing it for a little while, yeah? Even though I'm not going to put it on the homework directly. Okay, once you've identified the forces, we can apply Newton's laws. Here we go. There are 3 laws, and the way that most people learn them is wrong, or rather, let me say, the common way of stating them in grade school, I find, leads to a bunch of goofs, a bunch of errors, a bunch of misconceptions. So please, learn it the way I teach you. I'm telling you this for a reason. First law, if an object is not accelerating, and only if an object is not accelerating, then the forces on that object are balanced. Look for this. This is very often a shortcut to solving a problem. Very often, half a second, very often students will miss that it's a Newton's first law problem, and they'll try to start applying all these complicated equations. And then you realize, wait, it's not accelerating, forces are equal, bazinga, done. Question? I'm walking along at a steady speed in a straight line. All the forces on me are balanced right now. Weight up, the normal, weight up, weight, for God's sake, normal up, weight down are balanced, and it doesn't actually take a force to keep moving steadily, except for biomechanical fact that our legs are actually complicated devices. But if I were just sliding along on a sled or whatever, no horizontal force. Here's another one. Here. This is probably a better example. To the extent that we can ignore friction, till it hit pneumonia over there, that was Newton's first law. Moving along at a straight line at steady speed. Now, of course, there was friction, so it's not perfect. But yeah, forces are balanced. Well, to the extent that we care about friction, this did actually stop to some extent. I do care about friction. I'm going to model it more precisely.
So is that what that means, like
Unbalanced
unbalanced?
is, yeah, they don't add to 0. Oh, here's another example. When I'm flying through the air, there's only one force on me. That can't be balanced. You can't balance one force with others. So I'm accelerating. Hey, how fast am I accelerating? 9.8 meters per second squared, yeah.
So the normal force being up and weight being down is the balance.
Well, they're going in opposite directions. If I'm not accelerating, then they're also equal magnitudes. But it is possible for normal not to equal weight. For instance, as I was pushing my legs up, normal was bigger than weight force. That's what accelerated me upward. Or for that matter, as I am coming to a rest, normal is bigger than weight to accelerate me from moving downward to moving not at all. Good questions. Okay, so that's if an object is not accelerating. Forces are imbalanced, no acceleration, constant velocity. If you got constant velocity, then forces must be balanced. What if you do have acceleration? Then the magnitude of the acceleration is F over m. The direction of the acceleration is the same as the net force. I wrote that the other direction. The direction of the net force is the direction of the acceleration. The magnitude of the net force over mass is equal to the acceleration. Magnitude-wise. Yes. You want to find the direction of the acceleration? The acceleration is in the same direction as the total force. If you want to find the amount of acceleration, what causes an acceleration? The acceleration is equal to the total force on the object divided by its mass. That's called the second law. We will very often multiply both sides by mass and say net force equals mass times acceleration. Okay, so again, all of kinematics, all we studied so far is to say, if you got an acceleration, how do you find the velocity? If you got acceleration and velocity, how do you find the time? What's the displacement given the acceleration and velocity? Blah, 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 blah. We never said what causes an acceleration. I just told you the acceleration is this, that, or the other. Here's how to figure out what the acceleration will be. Ready for the first two? Oh, sorry, done with the first two? Yeah? Third law is slightly different. Third law is the interaction law. First two laws are all about how does an object interact with forces. Third law talks about how two objects exchange forces with each other. The essence of this is to say that every force is actually two forces. One force acting on each object in the interaction. Whenever an object A exerts force on object B, B also exerts an equal magnitude, opposite direction force back on A. Try this for a second. Clap. Both of your hands feel the clap, right? If both of your hands don't feel the clap, then see a neurologist, right? There is nothing you can do to have two hands clap and only one hand not feel it, and only have one hand feel it, yeah? Right? No matter if you put one hand stationary and the other move into it, or clap real hard. Wait, if you're clapping real hard, you're just clapping real hard, right? There's no possible way to clap hard with one hand and soft with the other hand. You're either clapping or you're not. Try it, try it. There's nothing you could do that makes your hands feel the clap differently. You believe me? That's the essence of the third law. Left hand interacts with right hand. They both feel the interaction the same way. This doesn't mean that the reaction is the same. For instance, the earth fell up to meet that bottle. This much. No, it's so small, of course, no one's ever going to observe it. This bottle exerts an equal force on the earth. This bottle weighs a Newton. This bottle exerts a Newton of force on the earth. When I'm throwing this up and down, the earth is recoiling and then falling back up to meet this bottle. Same if I jump. The earth just fell down, was pushed away, and then fell back up to meet me. It's just my mass is so much smaller than the earth. The acceleration of my tiny, insignificant mass is huge compared to the earth's acceleration. Yeah? Does that make some kind of sense? So the third law, you cannot clap without both hands feeling. You cannot punch somebody in the face without a lawsuit or without your knuckles getting bloodied. Yeah? Right? Every time two objects interact, they both feel pushed the same amount, even if the reaction is different. Yeah, if the result is different. Yeah.
On an object, if it's just like on the ground, just that stands up as how are those forces?
So if an object is sitting on the ground, there's an object sitting on the ground, that says that if this object is being supported by the ground also feels pushed back by it. And in an equal amount. Or, for example, if you stand on a scale, the scale registers your weight. How does that happen? Your weight is an interaction between the planet and you. But you push down on the scale with a force equal to your weight. The scale pushes up on you with a force equal to your weight if you're in balance. If you're not, yeah? Hey, incidentally, did you guys know scales don't measure weight? Scales measure normal force. Scales don't measure your weight. Your weight is a force between you and the planet. That's all. Nothing else. Forces are between two objects and only those two objects. No scale has ever measured a weight ever. Scales measure how hard you push on them. I mean, you could test this. Jump up and down on a scale. What happens to the needle? Is your weight actually changing? No, the scale is measuring that there's a different normal force exerted on it. If you stand stationary on the scale and nobody else has their toe on the scale, then there is a force equal to your weight going down on the scale. But it's not the weight force that the scale feels. It's the normal force. I'm talking too much. Let's do some problems. Ready? You need two equations. Weight equals mg. Net force over mass equals acceleration. Got those? Here, you can do these problems. Here's BCD in the Google form. Net force over mass equals acceleration. And weight equals mg. And have you wrestled with doing your first force problems for how long? How long do you want? 10 minutes? 8 minutes. Let me give you 8 minutes because this is your first time. You will probably need some handling. 8 minutes by the clock, and then I will give hints. Give me your best shot on these 3 in 8 minutes.
Be quiet in here. Talk to each other. Help each other out. Don't let ideas off. And help.
What are units for tension? What are we doing?
Every force is measured in newtons. The unit for every force is the newton. Forgot it was. There are doesn't exert force inside in this ball. Of course. So there is a top support. There are two forces that act on it. Mass is not a force. Weight is a force. The weight force, sure. What else? Yeah. Starting with the total. Accelerator? Acceleration is zero, the force must be. Doesn't mean that every force is zero. The total. Weight is not 55. Weight is 55 times G. Mass is 55. Weight is not 55. Weight equals mass times gravitational. 530. Correct. The mass is. What's the weight force? Weight equals it's time. Weight is 530. Got it. Got it. The only way for her not.
How do you find
Up minus down. What pulls it down? All up to my God. What pulls me down? Anyone studied the Bible? No, no, that book?
No, I'm sorry.
Okay. You should be. What was that? Correct. Are they accelerated? So what do you know? Force people. So what is it? Acceleration. Total forces. They're in balance. If there's no tension force, the fall. If I've got positive I have an answer.
So I use Netflix as a
What is the total? Fun. Good. Now what goes into that total? What forces add up to make that total?
strength and gravity.
Call it tension. Sure. And weight. Tension up, weight down equals something too.
So what I'm wondering is I have to add the weight to this to get accepted. Okay.
Okay, let's see what people got for BC. Hey, a lot of correct answers. Not every correct, but let's reason through this for a second. Here's how the expert does it. For B, Are we accelerating? For C, are we accelerating? Both of these are Newton's first law. What do you know when there's zero acceleration? What do you know about force? What forces act on the gymnast? Tension and gravity, or tension and weight. Okay. So if tension balances weight, then what are their respective magnitudes? How could you find the tension force? It's equal to the weight. Right? If tension balances weight, that is to say tension up minus weight down is equal to zero. Is total is zero. There's no net. So if tension minus weight equals zero, then tension equals weight. What's the formula for weight? 530 newtons is the correct answer for both B and C. Question?
So anytime we see like that big 5 kilograms of stuff, we should assume that's not.
Wait, say it louder.
Sorry, that might be saying. Every time we see like that estimate of like the 55 kilograms, then that's gonna be that's a mass.
Kilograms always measures mass. Kilograms is not a weight. Common jargon says I'm going to weigh something on a scale. Oh, this weighs 5 grams. No. Mass is 5 grams. Newtons measure weight. Every force is Newtons. Okay, so this is a very step-by-step process. I want to make sure that everybody's following along here. Are you all truly comfortable that there are only 2 forces acting on the gymnast?
Yes.
Tension up, weight down? Are you okay that tension acts upward? Really? Several students last class said, I thought tension is downward. They were imagining the rope being pulled by the gymnast. The gymnast does pull downward on the rope. By Newton's third law, then the rope pulls upward on the gymnast. So if the rope gets pulled down, then the rope pulls up. Okay, so what I would do at this point is anytime you can identify the forces, you can write a total force expression. If there are 2 forces on me acting up and down, I could say the total force is just the ups minus the downs. I might also sometimes re-express this as the wins minus the losses, but for B and C, they're both balanced. Okay? What is the total force if we're not accelerating? So I could say total force equals T minus W equals 0. Comfortable with that?
Wouldn't there be extra tension on the rope for you to be able to find?
Nope. Nope. Here's one of the deep laws of physics that Galileo Newton discovered. Inertia keeps you moving as you were. It doesn't take a force to move. It takes a force to change your motion. Now, your muscles are complicated biomechanical devices. Your muscles will be starting and stopping and exerting more and less than 530 newtons in a complicated fashion. Again, muscles are not simple devices. However, on average, the average total force exerted by rope on you, by your muscles on the rope, is 530. Again, for everybody's sake, everybody think about this for a second. It does not require force to move. It only requires force to change motion. Profound law. Yeah, question.
For B, for those
I rounded. What's 55 tell you? What is kilograms? What does it measure? Mass. What is the weight formula? $55 times 9.8 is 530. Is good? Wait, I feel like I dropped in the middle of something. Are you guys really actually comfortable with B and C? Now for D, we do have an acceleration. Does that change T or does that change W? When you accelerate, do you lose weight? Does that change your mass? Does that change the gravitational field? No, but T does change. I would say total force is now nu T minus same mg. So I have an algebraic expression, T minus 530 newtons. Okay, where do I use net force in for the acceleration equation? Net force over mass is equal to acceleration. I've given the acceleration and given the mass. I can find the other forces. T minus 530 over 55 is 1.3. Solve the solve. Six 30, 610, 6 something, 610? 610. Question me. Do you need help on the algebra? Who wants me to walk through the algebra? Oh, cool. Question first.
Was it not like it's not two different forces, the tension and the acceleration?
No, acceleration isn't a force. Acceleration is a result of forces. Hey, that's an important common misconception. Think about this for a second. Motion isn't a push or a pull. Motion happens because of pushes or pulls, or rather, changes in motion happen because of pushes or pulls, but the acceleration itself isn't a force. Acceleration is the result of forces. Don't get them confused. One is cause, one is effect. Are you comfortable with me solving this? Does anyone want algebra shown? Yeah? Okay. So we've got a fraction. We've got a fraction, T minus 530 equals 1.3. The first step I would do to algebraically simplify is get rid of the fraction. How do I get rid of the fraction? Clear the denominator. Multiply both sides by 55. Left side simplifies. Right side 1.3 times 55. Now what's attached to T? The T is attached to a 530 by subtraction. How do you get rid of a subtraction? Yeah? Is good? Question?
What's T representing?
Tension. Ah, okay. Where do you get T minus W equals 0 from? Ups minus downs is a total vector. So just like when I had a total displacement equals my motion to the right minus any motion to the left, I can say the total force, if I'm adding T newtons up and weight newtons down, is T minus W. Sometimes I will write upward forces as positive, downward forces are negative. Sometimes, if I am thinking about the direction of acceleration, I know the direction of acceleration, I might simplify this to just the forces that accelerate minus forces that oppose. So winners minus losers. Sometimes it's how I write net force. Now, are you okay with that? Every time you have forces acting on an object, think about which are acting in the direction of motion and which oppose the direction of motion. Good, honey got it. Any other questions about how you get net force? Okay, let's do another. Weight versus mass. Don't put the text. This is question E. Just write the number, 1, 2, 3, 4. And let's do this individually. No discussing. Hey, better than the 3 o'clock. Okay, everyone please vote. If you haven't voted, I'm guessing you're asleep. So let's talk about this. How did your chemistry professors tell you what mass is? How did they describe mass in chemistry class? What is mass? Other than what Catholics go to?
How much?
How much does something you have? Does that change based on where you are? Going in a big rocket, change how much of you there is? Maybe if you throw up. Right? Right? How much of you, that's just a property of how big you are, how dense you are, what kind of objects you're made of. Mass does not change going to the moon. But if gravitational field changes, m times g is smaller. Weight absolutely does change. You may have seen the movies of the Apollo astronauts bounding around like big white expensive bunnies on the moon's surface. The force that their leg exerts are equal to here on Earth. They're able to make these big giant leaps on the moon's surface. Although I think they found it awkward to do that in case they fell. I think they mostly kept it small, but you see them floating around a bit. Slow motion, it looked like. Less acceleration, smaller weight. The correct answer is 3. Mass don't change unless you change the thing itself. Weight depends on where you are. Okay, let's see what time it is. It is 5:20. I have you until 5:45. Do 2 more. 2 more problems and we'll try to choose some. Here you go. Where's that go? Turn to your neighbor. This is question F. Real fast, the one and only thing you need to know about tension is how much force a rope exerts. That's it. That's all you need to know about tension. Tension is the force exerted by a rope. No. No, the rope goes over the pulley. But then the rope's not really over the pulley. The rope's just dangling. The rope's not going to be over the pulley for long. And anyway, if they're suspended there, it means they're not falling. If you just have a rope dangling over the end of a pulley, mass on one end is zoom. Oh, but I didn't mention any. No. Opposite sides of the rope have different. Hey, what did I tell you? 50 what? Is this kilograms or newtons? Did I tell you W or did I tell you M? W is 50. What's M? This is divided by 10-ish. So the 5-kilogram boxes, for what it's worth. I have a fair number of people multiplying stuff by 9.8, presumably by habit. Okay? But don't just multiply anything you see by 9.8. This is not mass. It is not WG. W equals mg. Carry on, carry on, carry on. Oh, people have all come to confusion. Okay, you're mostly wrong. And here's how to prove it. Draw free body draw forces on one of the boxes. What two forces act on the box? Weight and tension. Is this accelerating? No, it's just gonna hang there, right? How much different is weight from tension? Which one's bigger? Third question, neither of them. If they're in balance, they're equal. So how much is the tension force? 50. Bing, bang, boom, you're done. Correct answer is 50 newtons. But what about this sucker? Who cares? This guy is also feeling 50 newtons. Again, I'm defining tension, describing tension is the force a rope exerts. Tension is the force a rope exerts. He's exerting 50 newtons of force. His tension is 50 newtons. That's it. No more to be said.
Isn't the rope attached to both of them though?
So?
It's not feeling both 50s at once, it's one rope.
So this guy is pulling on this rope with 50 newtons. Therefore, by the third law, the rope pulls him with 50 newtons. This guy pulls on him with 50 newtons. Therefore, by Newton's third law, this rope pulls on him with 50 newtons. That's true. The rope is pulling on the objects with 50 newtons of force. That's true.
A total of 100
No. No. The total force acting on the rope is 0 newtons. The total force acting on the rope is 0 newtons. There are equal masses on equal sides exerting equal forces. Let me give you an example. Miss, can I have you push on his left shoulder a little? He's applying, feels like about 75 newtons. I'm applying 75 newtons. Did you accelerate because of 150 newtons?
No.
No. What was the total force on you? Total force was 0. Total force is 0. Does that mean she wasn't pushing on you? No. How hard was she pushing on you? Exactly. The push exerted by a rope is 75 newtons. Your shoulder was pushing back on her with 75 newtons. Not 150. You were exerting 75 this way, 75 this way. You were getting pushed 75 this way, 75 this way. Not 150. Total force is 0. That's the sum of two individual forces. Each individual force is 50. Yeah.
So, just as a recap, since there's no difference between the tension and weight because there's no acceleration, it's just the weight of the box.
Yeah.
The tension. So if there was acceleration, it would be different.
Yes. Actually, next time we'll do case where we have different masses box. That ends up being an interestingly complicated problem. Hey, here's another way to prove this. What happens if I just grab the rope? Would that change a darn thing? Would just holding onto the rope change anything? Yeah, I'm not going to do anything to the rope. I'm just going to hold it there. I'm not going to change the tension of the rope, right? How much force is the rope exerting on me? 50 newtons. How much rope is how much force am I exerting on the rope? I'm pulling with 50 newtons. The tension in the rope is 50 newtons.
It's asking if you just hold on to the rope.
Yeah, if I just grab the rope, stationary, everything's stationary, just hold it.
Without the second box.
Who cares about the second box? The second box is ignorable. I mean, you could tie this to the ceiling. Nothing changes with the tensions. What force is acting on what force is the rope exerting? 50 newtons to support this. Yeah? Hey, what happens if you apply 50 newtons on one side and 0 newtons on the other side to the rope? It's going to accelerate to the speed of light. The rope is presumably massless. That's what I usually say. If m is basically 0 and you apply a total force to the mass, total force to basically no mass, acceleration is going to be off the charts. Does that make sense? We apply Newton's second law. If the force on either end of the rope is different, the acceleration is basically infinity. To the extent that the rope's mass is ignorable. The rope's TLDR, ropes always exert equal forces on opposite sides. That force is what I call the tension of the rope. Not twice it, not half it. Good? Yeah, we'll see more practice with this. One more. Last one. What is this? F? G? This is G. Just put 1, 2, 3. You don't need to type it out. You don't need to say option 3 or whatever. But you can work with your neighbor this time. Ask yourself this, which direction is it accelerating? Hey, point to me, not to me. For me, point which direction the elevator accelerates, up or down. Slowing down while moving down. Slowing down while moving downward is accelerating upward. Velocity graph. If we're moving downward, what do you know about the velocity? If the velocity represents downward motion, we're talking about negative values. If he's slowing down, which direction is he aiming? Towards the x-axis or the t-axis. Positive or negative slope? Upward acceleration. Alternately, you could say things slow down when their acceleration and velocity point in opposite directions. Remember that? If the velocity is downward, the acceleration has to be upward to slow it. Okay, so if it accelerates upward, which direction is the total force? Come on. If it accelerates upward, which is the total force? Which force wins, the upward or the downward force? Which force is the upward force? Correct answer is 3. Tension wins. Tension is the bigger. Yeah, a good number of people got that. All right, you should actually have a fair number of questions. I will stick around for a bit, but also, you guys be sleepy. Hey, I need you to bring your A game on Wednesday. This, I'm doing introductory problems. We're going to continue from here, but it's going to get harder, more challenging. I want you guys to bring your A game on Wednesday. Wake up, take a Red Bull or whatever, and see me on Wednesday. I will stick around to answer questions, though.
But it's not about like, so I know your feet.
I don't know. Yeah, I wouldn't even want to no. Well, actually, this works. If you look at all I want to do. That doesn't bring in grant money.
Thank you. Have a nice day.
Sure.